Alright, so here we're going to begin 9.1, Graphing Quadratic Functions. Here's the why. Quadratics are projectile motion. They are also used for business. They're used for many things. You've previously watched intro videos to get you excited for this chapter, showing you different things with quadratics. We had football punts, we had basketball shots, anything that's getting launched up into the air. And then parabolas are also used often in architecture for the St. Louis Arch or the two arms that make the M in McDonald's. We saw the videos on that. They can tell us things such as how high or how far did something launch. They can help us maximize profits in business, minimize expenses. You use them a lot for that. There's minimize expenses. Because if you're running a business, that's typically what you want to do. You want to maximize how much money you're bringing in and minimize how much you have to spend. All right, so here's some vocabulary for this here. Now, here's what makes something a quadratic function. For something to be a quadratic function, it must have what's called a quadratic term. And the quadratic term is something that has an exponent of 2. It can also have other parts, such as a linear term, and then also a constant term. But it must have the quadratic term. If it doesn't have a linear term or a constant term, that's okay. Sometimes we'll just see a function such as y is equal to x squared. It's still quadratic because it has a quadratic term. If it has a linear constant term, that's fine. But that x squared is what makes it quadratic. All right? So, here's what we've got. The overall shape of this is called a parabola. So all three of these curves you see are parabolas. There's two types. They can open up or they can open down. All right. Now, other things that are familiar with them are concepts like this. We've got y-intercepts. They will still have y-intercepts. A really key point, this is going to be a big point of focus moving forward, is this guy right here. Either the very bottom or the very top of the parabola is called a vertex. We'll do a lot of discussion based on vertex. These are going to be symmetrical. You'll see this dotted line. The dotted line isn't a part of the graph, technically, but sometimes it'll be shown. It's called the axis of symmetry. And what it does is it divides the quadratic into two equal parts. It's essentially what makes projectile motion the concept of what goes up must come back down. Because they're symmetrical, quadratics are symmetrical on either side of the vertex. And then there's two options. You can have what's called a maximum, which is the point all the way at the top, or you can have what's called a minimum, which is a point at the bottom. And so if we're concerned about how high a football punt went, we're looking at the maximum. If you were working on a business problem and you're trying to minimize expenses, you want to look for the minimum. We're going to come back and take a look at this business problem once we learn a little bit more about quadratics. We're going to spend a lot of our time graphing quadratics. We're going to see one here. You're going to need to see many more to help you understand, and you'll have to do several to understand as well. The next section we'll look at is still going to be graphing. So if you are having a hard time here in 9.1, when we pick it up again in 9.3, you'll see that we get more and more practice on it. So we'll be here for a while. Now, here's the first thing we're going to need to do. We're going to need to understand what standard form is. Standard form for quadratics is y is equal to ax squared plus bx plus c. So they gave us an above example here, but it needs to be rewritten as 2x squared, then the plus 8x plus the 2. These weren't in the right order. We need to get it into the right order. And the reason that we need to do this is because when we're working with quadratics, we're going to use formulas that are going to use the a, b, and c values. So here, our a is 2, our b is 8, and our c is 2. The main reason we need those is the formula to help us find the vertex. All right, to find the vertex, it's a two-part process because the vertex is a coordinate point. The x-coordinate of the vertex is negative b divided by 2a. That will tell us the x-coordinate for our vertex. So let's do that. I'm going to write out a blank formula. Negative b divided by 2a. All right, so this is the negative b divided by 2a. Our b value from up above was 8. Our a value was 2. This is going to tell us the x-coordinate, which is going to be negative 8 divided by 4. To get that the x-coordinate for our vertex is negative 2. Now, in order to find the y-coordinate, what you'll need to do, and you'll hear this a lot, you need to plug in x to find y. And what you plug x into is the original equation. So this guy. So where everywhere that I had an x, I'm going to replace it with negative 2. When we do that here, negative 2 squared is 4. 4 times 2 is 8. Then we get a minus 16 plus 2. And when we put all this together, this is going to allow us to find out our y-coordinate. Our y-coordinate is 8 minus 16, which is negative 8, plus 2, to get a negative 6. Okay? So here's what that's going to allow us to do. Once we find the vertex, we now know we've either found a point that's going to look like this or a point that's going to look like this. Now, we haven't learned to decide whether quadratics open up or down yet. We'll continue to learn about that, but we've learned how to find either that minimum point or the maximum point. We're going to use that in the table. We're going to put the vertex in the center of the table. Now, the reason that we're going to do that is because of symmetry. I'm going to go ahead and graph this vertex. Negative 2, negative 6 lands right there. The reason we want to put the vertex in the middle of the table is because if I continue to make this table, we're going to see that we get symmetry. There's an axis of symmetry, or a line of symmetry, that passes through the vertex. Right? Because anytime we find a vertex, there's an invisible dotted line that crosses through it, that splits it into two equal parts. We can use that to help make the graph much quicker. Let's also talk about the y-intercept. Y-intercept is always 0, comma, right? And so, if we think about any time we plug in a 0 into standard form, if we plug in a 0 for x, you'll notice that everything cancels out except the c. So the y-intercept of a quadratic is always 0, c. Our c value from up above is 2. Now, down here in the table, we now know that this point is 0, 2. And due to symmetry, if this is 2, this number here is also 2 because it must be symmetrical around the vertex. So we can come graph this. 0, 2, and then also a point of symmetry will be right there. All right, and see how they're both 2 spots away from that center line? Now, in order to find other values, what we're going to have to do is plug it into the original equation. But here's the good news. I don't need to plug in -3 and -1. I can actually just pick one of them because they're going to be the same. So we just need to pick one of them to plug back into the original equation. Now, I'm going to pick the -1 because it's a smaller number and easier to work with. -1 squared is 1, times 2 is 2, minus 8 plus 2. 2 minus 8 is -6. -6 plus 2 tells me that my y is equal to a -4. So now I have this information to graph. We had -3, -4, and we had -1, -4. Now you might notice that it's not a straight line. These are different. This one increases by 2. This one increased by 4. So you're not going to be able to take a ruler and connect these points. Quadratics make a curve like that. Now that one's not drawn super nice, but they make those U-shaped curves that are symmetrical at the vertex. So graphing quadratics are definitely more complicated than graphing linear equations, but that should make sense because these have ups and downs and highs and lows, and lines were just lines. So they are more complicated to graph, but they'll also allow us to do more interesting scenarios with the math. So here's going to be another example of where it's not having us find a whole graph, but it is going to ask us some key pieces of information. And here's what they are. It says find the x-coordinate of the vertex and find the y-coordinate of the vertex. You need to memorize this formula, that x of the vertex is -b over 2a. And in this case here, our a is -2, our b is 12, and our c is -5. So with this, what we'll have to do is plug it into the formula. The x-coordinate of the vertex will be -b divided by 2a. So we'll get a -12 divided by -4 to get that the x-coordinate of our vertex is 3. To find the y-coordinate, we need to go back to the original equation. And everywhere that we have a parenthesis group, we need to replace it with that 3. 3 squared is 9 times a -2 is -18 plus 36 minus 5. So here we'll get an 18 minus 5 to get the y-coordinate of our vertex as 13. All right. So before we talk about domain and range, we need to talk about this box here. And it says, how can you remember the way to use x squared term of a quadratic function to tell whether it has a minimum or a maximum value? Here's what that's asking. We know that our vertex is at 3, 13. But what I haven't taught you yet is, does this quadratic then open up? Or does the quadratic open down? Right? We don't know. And that's going to impact the next question of domain and range. Here's how you do it. If you have a positive x squared term, so if y is equal to a positive x squared term, you open up every single time. It doesn't matter what else happens here, right? This could be anything else. B and C can be any other terms at once. It doesn't matter. As long as you have a positive x squared, you will open up. Which then means if you have a negative x squared, regardless of what your B and C values are, you open down. So in our case here, we have a negative in front of our x squared, which means we are in fact this scenario to where our vertex is at 3, 13, and we open down. So here's what domain and range are. A quick review. Domain is all possible x values that you could expect to see on a graph or a table. So this one's very easy. Easy points all chapter long. The domain for all quadratics is that symbol that meant all real numbers. What that's telling us is that, if I wanted to extend a table, both higher and lower, in the x column, I could type in any number that I want. Every number for x will work. This graph will eventually go everywhere to the right and everywhere to the left. It'll hit every x value. However, the range is not going to be the same. It's not going to be all real numbers. Because if we look at our case, I don't go to every y coordinate ever. I have a maximum. I stop at some point. So what we want to say for this range is we're going to say, hey, our y values are always less than or equal to 13. Because 13 is the very tallest point of this quadratic. And then otherwise, we're always smaller. So your y values are anything less than or equal to 13. So the way that this impacts the range, if you have a quadratic that opens up, right, and you have some vertex, x comma y, your range will be y is greater than or equal to this y coordinate. If you have a quadratic that opens down with some vertex x comma y, your range is going to be y is less than or equal to whatever that number is. And what this is saying is, if you were trying to punt a football and you wanted to get it 70 yards into the air, or 50 yards into the air, how you wanted to get it. If you punted a football straight up and it only went 20 yards into the air, and your goal was for it to get to 40 yards into the air, you didn't make it, right? The range of your football was y is less than or equal to 20. It never got any higher than 20. So that's what range can help you do, is answer those types of questions. Did it go high enough would be the range. So let's come back. We're not going to look at this problem. That problem didn't pan out the way I wanted it. We're going to look at this from a business perspective. That way we're not always just talking about punting footballs or shooting basketballs, but other applications as well. The manager of a symphony computes that the symphony will earn negative 40p squared plus 1,100 p dollars per concert if they charge p dollars for tickets. What ticket price should the symphony charge in order to maximize its profits? Here's what this is going to look like if we were to make a graph. There's going to be some type of maximum or vertex. That's what we're looking for. Now, here's why business often turns into quadratics. If this is price of tickets, and this is profit, it's going to make a quadratic scenario, and here's why. If you sell, or if you charge $0 for your tickets, you're not going to make any money because you didn't make any profit. However, if you say, my tickets are going to be $1,000, you're still not going to make any money because no one's going to come. If your tickets are too expensive, or maybe even $1 million, if you pick something too expensive, no one's going to buy your tickets, so you're not going to make any money. But somewhere in between, and this wouldn't actually be, $1 million, that's too large of a number. But somewhere in between, there's a happy medium, right? So this right here is essentially the fair price. If you price things fairly, you can sell the most amount of tickets. Right here, if you're charging too little for tickets, you're not going to make enough money. But as soon as you start to charge too much, not as many people buy it, so you still don't make a lot of money. You're trying to find this. How much should you charge to maximize your profit? Right? If you think about it, that should make a lot of sense. You can't charge nothing. You can't charge too much. You need to find the happy medium in between. So in order to find that profit, we're looking for the vertex. And the way to find a vertex is negative b over 2a. So, based upon our equation up top, our a value is negative 40, and our b value is 1,100. If you're wondering where the c value is, it's 0, because our y-intercept is at 0. So let's do the formula. Negative b divided by 2a and when we calculate this, for this particular theater symphony, they would want to charge $13.75. So what that means, if we were to make a quick graph of this, it would start at 0. The point that our axis of symmetry would be on would be at 13.75. Now, to calculate how high to make this curve, we could simply plug in 13.75 back into the original function, which would be negative 40 times our maximum amount that we should charge. So when we do that and we calculate it, and this should be squared, we get this. I'm typing it in. 7,562.5. So they're up here at somewhere around 7,600. Sorry, 700. No, it is 7,600. That's roughly kind of where there will be. So for this one, the range would be describing the amount of profit that they could make, and that's why range is important. The profit that this symphony is going to make is going to be somewhere less than $7,562.50. And if you think about it, that should make sense. They could make no money, or they could make any of these other values in between. But all of these different amounts of money that they could make, depending on ticket price, will be less than whatever that y-coordinate of the vertex is. So we'll continue to study a lot more on quadratics. It might be helpful to watch certain portions of this video again, because it's definitely a little more complicated than linear equations.